Hi, welcome to my channel on technology space with machine learning and artificial intelligence. So today's topic is digitalization. So let's try to define what is digitalization. We should know often these words are different things for different people, but if you're a part of a research group or research communication, you may need some level of consistency, yet having some level of scientific content behind these definitions. So this presentation or this discussion is a starting point of having some level of clarity in these wordings. So before I define the digitalization, let's define what is digital. You probably heard about the word called digitization. I think that is somewhat simpler one to define. So let's look into the question of what is digitization. Often when you transform information into a digital format, which can be a data file, that can be considered as the process of digitization. So for example, if you're transforming written information into a data file in a computer, that is the process of digitization. So since we are clear on that definition, let's revisit that question of what is digital. Before I answer that question, let's talk about digital and analog systems, which you may have heard before. Most of the mechanical systems and some electrical systems can be considered as analog systems because they are working in a continuous time domain. So because of this same reason, we consider those as continuous time systems. If you're coming from a control system type of a background, you're probably familiar with these continuous time systems. And then opposite version of that, there are discrete time systems or digital systems also there. For example, computers and microprocessors work in a different time intervals or time instance. So because of that working conditions, we define these systems as a digital or discrete time systems. So if you're trying to measure this behavior of such systems, probably through sensors, you often end up with different types of signal. For example, if you have an analog system and you try to use some type of a sensor to measure one parameter in that system. For example, in an engine, if you have a fluid flow, you want to measure the temperature, pressure in that fluid flow. That can be a continuous time signal. So that means the time is continuous in the most simplest sense. But if you want to measure these signals, often what happens, you probably connect some type of a data acquisition system into these sensors. And these data acquisition systems are digital systems. They measure these parameters often in discrete time. In general, what it does is it has some sort of a processor which starts every, let's say, for example, 5 milliseconds. And every 5 milliseconds, it measures that signal value. So what happening through that process is you kind of discretize that signal. Even though it was coming under continuous time, you're measuring in a discrete time intervals. Because of that, you discretize that signal. But then you want to recreate that signal in a continuous time because that information is useful. Then what often happens is you will keep that same value which you have measured in a single instance throughout that small sampling time period. So that eventually create this discrete time signal. Now we can imagine you had an analog or continuous time system. You measure a continuous time signal with some sort of a microprocessors, and then you end up with a discrete time system, yet it's continuous. So now we can see the difference between this analog and digital system versus analog and digital signals. So I would think then it's easier for me to explain what is digital. So the meaning of digital is discrete. So this definition is really important because that would dominate quite a lot of definitions we're going to discuss in later slides of this presentation. So what happened during this process was we had a continuous time signal from analog system. You try to measure it, you end up with a digital time signal, and you can imagine that is kind of coming from a discrete time system. So since already we defined the digital, so in a way the digital means the discrete. So this discreteness is the digitalness you often bring into these systems. So the next question would be, can a digital twin exist? So the problem in this question is, let's think about, you have an analog system. If you want to model that analog system, you often use continuous time differential equations. So here one example of that as just a general representation. But if you want to create a digital model or discrete model of that system, you end up with the discrete time differential equations. So the continuous time differential equations and the discrete time differential equations are working in two different domains, and there are quite a lot of things not common for these two domains. So because of that same reason, it would be almost impossible for you to develop discrete time differential equation or discrete time model for an existing continuous time system. At least it wouldn't be a twin. It would be some sort of a digital model, but it wouldn't be a twin. So, but then the wording of digital twin is already out there. As you know, there are many research calls on that. Technically or scientifically, it is almost impossible to create a digital version of a twin because of this discrete and continuous time domain differences, but that ship has sailed. So we kind of have to live with it and then try to bring our own definitions into these digital twin. So since I had a small discussion on the digital twin, I will revisit that at the end. But let's try to define what is digitalization. That was the main question we had in the beginning of this presentation. So the digitalization is a process of transforming data into useful information, then that into a smart decision. This is more into industrial sense. So let's go through that process step by step. So initially you will have some type of industrial systems, and then often these systems associated with industrial IoTs. These can be sensors, data acquisition systems, and then other things which you utilize towards measure the system behavior. So these industrial IoTs collect a large amount of data. Often these things categorized as big data, and the wording of extreme data also out there. So if you have a data sets, the next step would be to store and these data sets in a proper format, which can be utilized in a later stage. So that can be done by this data management layer. And from data management to the data analytics, this is where you try to analyze the data, but that wouldn't be a straightforward path due to many challenges. These challenges has been categorized as 4V, which is data volume, data velocity, data variety, and data veracity. Data volume often related to the scale of the data, data velocity often related to the stream of the data, and then data variety and veracity. Variety is different forms of the data, and then data veracity is uncertainty in the data. I would believe these data volume and velocity issues can be handled by the data management layer, but when it's come to data variety and veracity, it would be handled by the data analytics. So when you coming to develop these data analytics, I would believe these domain knowledge will play an important role, because often these analytics can be specific for that specific domain. I wouldn't think these analytics can be generalized in a large scale. So because of that reason, you have to get involved large amount of domain knowledge into these analytics. So then the analytics can be utilized towards the useful information. But then this useful information create the advanced knowledge. And then this advanced knowledge would result in industrial intelligence. And then industrial intelligence would be resulted in smart decisions in industrial applications or industrial operations. One more thing to be mentioned in this process, since I have mentioned the data analytics, the digital twin often going to be a part of these advanced data analytics in this digitalization process. So let's come back and revisit this concept of digital twin. I would have a separate video set or video clips about the definition of digital twin and how to develop that. But I will give you a basic concept of the digital twin in this discussion. So the digital twin for us is understanding the system behavior from data sets. So how can we do that? I think if you stick around, I would discuss how these data sets we transformed into a highly complex mathematical structures, and then these mathematical structures of the data sets itself become a digital model for these analog systems in many industrial applications. So that's pretty much it on this topic of digitalization. Hopefully you have enjoyed the video. And as I have mentioned, there will be many main and subtopics related to these machine learning and artificial intelligence will come in this channel. So if you're interested, please stick around. Thank you.